Today we're going to take a look at how to find volume using washers. Alright, we're going to start by just finding the volume of this one washer. Now, the washer we can look at as two cylinders. One where, starting from the center out, we've got one large radius that we'll call big R, and then the hole in the middle creates another cylinder with a radius that we'll call little r. So the volume of our washer is going to be pi big R squared h minus pi little r squared h. And we can factor this by taking the pi and the h out. And then in the parentheses we've got our big R squared minus little r squared. And I'm going to rearrange these terms and put the pi in front. So we've got big R squared, little r squared on the inside, and then h in the back here. So again, the volume of our washer, we've got pi big R squared minus little r squared, whoops, and h on the outside. And now what we're going to do is we're going to take a look at a couple of functions and then bring it back to the washer. So let's take a look at y equals radical x, and then at just the first quadrant of y equals x squared. And we are going to use the x-axis as our axis of revolution. And now imagine that we're taking this area and we're going around the x-axis. We're going to end up with a three-dimensional object. And we're going to try to find the volume of that three-dimensional object by using our washers. We'll use a bunch of washers, find the volume, add them up, and that'll be a nice approximation of the volume of the three-dimensional object. Now here, this rectangle becomes our washer, and we're really looking at this cross-section of kind of the side of a washer, where this is our big R, and then this little gap here is going to create the hole in that washer, which is given by our little r. And then this distance here is our h, which we can also think of as our delta x or dx. Alright, so what we want to do is find the volume of a whole bunch of washers and add those volumes up. So that will be the integral of pi big R squared minus little r squared, and then h we're going to use dx. And then we're bounded by some interval from a to b. So I'm going to rewrite this a little bit because I can take that pi out, which is how we usually see it with the constant in front, from a to b of big R squared minus little r squared dx. So let's use the information we have from our graph with these specific functions. Our volume is pi times, our interval starts at 0, and then these two functions intersect when x is equal to 1. If you're not sure of that, you can set our two equations equal to each other and solve. Big R is the distance from the x-axis to the red function, the radical function, so that's radical x squared, minus little r is the distance from the x-axis to the green function, and that's x squared squared dx. From there, you are going to either evaluate the integral by hand or use a calculator, and we should get 3 pi over 10. Now there is a special case. Let's take a look just at the first quadrant, and let's just use the graph of y equals x cubed. And again, we'll go from 0 until, let's go with 4. And let's find the volume of the region between y equals x cubed and the x-axis, again revolving around the x-axis. Now here's what our rectangle will look like. And notice we have a big R, but there's no gap. There's no little r. So what we have is a full cylinder without the hole in the middle. So now our volume is pi from 0 to 4 of big R squared. Big R is x cubed squared, still minus little r, but now little r is 0 squared dx. So this is a special case of washers that we call volume by, instead of a washer, we call it a disk.